All right, let's consider next material removal. These are among some of the most popular processes, fabrication processes that are found particularly in the prototyping stages. You also find them in short run as well as full production, but some of these again are very, very commonly found in prototype development and also modeling, so they're certainly very worthwhile knowing about. You can see there's quite a few of them, so sewing, that would be just the simple act of taking stock material and cutting it close to the net shape that we're going to develop, so you can think of this as just a means for quickly separating a starting piece from the source stock. Drilling is perhaps the second simplest processing here, and it consists, as you might well imagine, of just using a drill bit in order to create a hole. Now, when we drill, we can also ream. Okay, that's another process, that slightly enlarges a pre-drilled hole in order to get a high accuracy final hole. Okay, we can also use the concept of, or associate, I should say, the concept of tapping here with drilling. Okay, so a tap will be used sometimes in conjunction with the drilling machine in order to create an inside thread by means of a tap, of the tapping process. Turning there is synonymous, with lathing, or using a lathe, and that is a quintessential method for creating solids of revolution. So again, this is something that we should be able to relate to rather naturally with our prior experience in SolidWorks. Milling is probably the king of the prototype shop, or the king of the fabrication shop. Again, primarily for low volume production, but also used in some other production scenarios. The milling machine is one of the most versatile pieces of material removal equipment that there are, and we'll look at a couple of pictures of that as well. Okay, grinding here in this particular context is used for material removal, particularly for metals that are very, very hard. So for high performance metals, where it may not be expedient to use conventional cutting or other material removal processes. Okay? Grinding, of course, can also be thought of in terms of achieving a smooth surface or removing burrs or things like this. And then at that point, grinding transitions into a finishing process, which is a whole different ballgame altogether. Now we're talking about very, very high precision working of a surface. Die cutting is another process that is used to remove material in a given shape, and the best way to relate to it is the proverbial cookie cutter that cuts into the dough there. There are sheet metal processes that are effectively the equivalent of die cutting, except we don't call them die cuts in sheet metal, we call them punching processes. And then another material removal process that is there again for completeness, like powder metallurgy. Before it's certainly very useful when you need it, but it's not common, I would say. Electrodischarge machining is what it stands for. It comes in two different varieties. There's wire EDM and plunge EDM. And again, not your typical shop floor or prototyping shop process, so we won't spend as much time on that, other than to include it in our list, again, for completeness primarily. Okay, so some pictures here to situate ourselves. There on the left, a very traditional bandsaw. Okay, so of course you can understand the bandsaw here is good for cutting straight or doing very, very wide circles, but clearly wouldn't be suitable to apply any manner of radius. That would be the job of a different material removal operation. On the right in there, a classical drill press. This can be floor mounted. They can also be bench mounted. They come in different varieties. And again, you will use drill bits as well as reamers and potentially also tapping tools. Here is a picture of a lathe. Okay, so the lathe, if you look in there, it has a headstock with a chuck that is used to hold the work or the part that is going to be turned. There's also a tailstock, and there all the way to the right that you can see, and that slides on a rail, and then there is a component there in the middle where a particular cutting tool will come into contact with the part. Okay, so this is a very, very useful piece of equipment, again, for any solid that is a solid of revolution in nature. You can create stepped features in there. You can apply chamfers, you can apply grooves, you can bore holes into the part, and we call those operations boring, when they're done this way as opposed to drilling. Okay, slight difference in terminology there. You can also apply tapers. You can even create screw threads if you're cutting the screw thread. Okay, so these are common use for a lathe. Here is a mill. The mill, like the lathe, can also come in the smaller varieties, which will be bench mounted, but generally you will find them floor mounted. These are very substantial pieces of equipment. Like the lathes, a lot of the mills are numerically controlled, which are known as the CNC mills and CNC lathes. The particular one that you see here would be a very, very simple bench mounted lathe. Just to illustrate the concept, this particular one has 3 axes of motion, so you can move the bed left and right and also in and out. And then you can, of course, plunge the cutting tool through its Z axis in there. Again, extremely versatile machines. You can augment the number of axes in there with the addition of a rotary table. You can generally go up to 5 axes with these machines. Of course, the 6th axis, would be the rotation of the tool itself. So unlike a robot in a CNC, you don't normally see 6 axes, or at least 6 independent axes. Okay, on your upper left in there, a bench grinder. Now, these grinders sometimes will come with 2 different wheels, for 2 different materials or coarseness, if you will, or there may be a grinding wheel and a polishing wheel. Okay, so very common piece of equipment to find in a machine shop. On the right in there, you see an example of a die cutter. Okay, so you see the die cutter itself mounted on a plank of wood, and those are very sharp pieces of metal that conform to the shape that is to be cut. And of course, this would be applicable to relatively soft materials or certainly thin materials. Okay. And again, if you were doing this in the context of sheet metal, then that would get its own technology and its own terminology. Okay. Which is, of course, the example that you see down in the bottom. That is an automated CNC sheet metal machine, and there are, again, many different processes. They have different names, but you can cut material, you can bend material in there, you can create louvers, various other things. So again, for products that are sheet metal centric, there's an entire industry, an entire niche market dedicated to them. Now, looking at the matter of joining in this whirlwind tour of manufacturing technologies, right? So joining comes in different flavors. We use welding when we want to generally put metals together. Now, welding also applies to plastics. Okay, and that is, in fact, at the very end of the sentence in there where you say ultrasonic. And so when you hear about ultrasonic welding, normally you're talking about the welding of plastics by means of ultrasonic vibrations. In the metal context, you would be talking about many, many different styles of welding. You could have stick welding, you can have wire welding or MIG welding as it's known. Yeah. You can have TIG welding, with or without a filler metal. You can talk about even friction welding and even other categories. Oxyacetylene welding is another technology that is used in there. And of course, all this amounts to heating the 2 materials so that joining occurs at the base crystalline structure. An adjunct to welding is brazing, which is not included in there, but in the case of brazing, you're not relying on the melting of the base metals, but rather you're adding a second metal in there that effectively acts as a joining agent in between the 2. Okay. You can imagine that with welding there are heating concerns, and that in fact can constrain the use of this particular fabrication technique in some cases. Okay. Soldering in there is a very specific application, generally done in the context of electronics manufacturing. So again, it is there for completeness, but not generally as applicable as some of the other processes that we're highlighting here. Okay. Of course, you can do bonding in there, and bonding generally refers to adhesive bonding, and that is done, of course, now you're talking about some chemical means, generally epoxies, cyanoacrylates. The epoxies generally two-part in there for high-performance applications, meaning that you have to mix two materials, basically have a cross-linking of a polymer in there in order to perform its bonding function. And then, of course, we have fastening. Fastening is perhaps should have occupied the first place in there, but fastening is, of course, done through bolts and nuts and rivets and other componentry that we've already talked about. If you picture it, to fix this in our mind, on the upper left, in fact, an oxyacetylene torch in there, so that would be used for certain types of welding. On the top right, a MIG torch, again putting perhaps two plates of metal together. You can see the weld bead there in the middle. These, by the way, are very accessible, rather inexpensive processes, very readily available in machine shops, and not very difficult to learn. Of course, like anything else, it has to be done with care and good supervision, but certainly very accessible in terms of processes that you might want to consider for your prototypes. On the bottom left in there, we see a couple of pictures related to bonding. So that would be a two-part epoxy product, and then, well, I guess what I'll call a bit of a hack, but a potentially useful application of bonding in order to join put in a fastening feature, a thread in effect, to a washer or a plate of some manner. And then down on the right, just as a reminder that fastening in here is probably far and away the most common of the joining processes. Okay, and finally we get to finishing processes in here. So let's review them quickly. So we have their polishing, painting, plating, anodizing, and heat treat. Okay, so of course we assume that we already have a part that's substantially finished, and all we need to do is impart to it some design characteristic that's desirable in some manner. Now that could be related to, for example, abrasion resistance, wear resistance, resistance to corrosion perhaps. Okay, a lot of times we paint, for that very reason. Okay, so steel is wonderful, inexpensive, but it has a nasty tendency to corrode. So painting will do that for you. We can also chrome plate something, perhaps even for appearance, not just for functional characteristics, but for aesthetic characteristics. Okay, we might want to impart a particular finish because of dimensional needs. Okay, so that would be the moving from grinding into polishing and lapping. Okay, and that's in fact how we get the very, very finest, the highest precision measurements, that can be had, through these processes. Even though they're categorized as finishing processes, they're mechanical finishing in nature. Some of these other processes have to do with electrical properties, even with thermal properties, perhaps with tribological properties, meaning reducing friction or having, as I said before, better wear characteristics. Okay. And then finally we have heat treatment processes, and heat treatment is done to modify the metallurgical characteristics of the part in order to obtain a certain hardness or a certain crystalline structure of interest. Okay. So some photographs again here to fix this in mind. We see a gentleman polishing a guitar in there. So that is a typical polishing wheel, and you can use a bench grinder for that operation. On the right we see an industrial paint booth. Okay, and paint itself, has it's a very, very well established niche market, and it can go from the very simple to the very sophisticated using electrostatic methods. Of course, there's a lot of prep that goes into painting, priming, painting in different layers, etc., etc. So very sophisticated industry behind and processes behind printing or painting rather. There on the left we see a chemical tank. Okay, that undoubtedly is being used for some manner of electrochemical plating operation or electrochemical treatment operation of some manner. On the bottom left in there you see some examples of color anodizing. Okay, so this can be used for treatment of aluminum. So, this is a typical thing to do to aluminum parts. And of course the color gives it an aesthetic dimension as well. And then some what appears to be some chroming operation there on those fastening components. Okay. And finally there on the right we see a picture of a heat treatment machine. So this is undoubtedly a conveyor oven of some manner. So you can see the pipes there perhaps conducting the gas for the flames in order to create the heat environment inside the chamber, and then probably a very slow moving conveyor that allows the parts to be subjected to certain temperature profiles, and that again has the effect of affecting the metallurgy of the part. Okay, so one more time. We have bulk formation, bulk deformation, material removal, joining, and finishing. Okay, so bulk formation processes, common suspects in there: casting, molding, okay, and rapid prototyping. Okay, bulk deformation, that's when we're talking about forging, okay, and extrusion processes, and sheet metal being sort of its own universe. Material removal, some of the most common processes are here that you would find in a prototype shop. Okay, so sawing, drilling, turning or the lathe, milling, okay, some of the most versatile machines again there. Okay, grinding, die cutting, and then sheet metal processes again on their own category as would be the EDM processes, electrode discharge machining. Joining processes, again, very important, fastening first and foremost, but we can also weld things together, we can solder them together, or braze them together, I guess we'll say, in the context of common metals for structural applications. Okay, bonding, that can be done with chemicals, with adhesives. Ultrasonic welding is a particular category for plastics. And finally, finishing that processes that enable us to give a very particular character to a part that is otherwise geometrically in its final form, again with the exception of some mechanical finishing whose only purpose is to increase the tolerance, the accuracy of the dimensions of the part.